Hello, I'm Borja Boutzon, and in this talk I will present a novel deep semantic segmentation method for unmanned surface vehicles. Unmanned surface vehicles, or shorter USVs, are small-sized robotic boats like the one you can see here. They are primarily used for inspection of difficult-to-reach areas, which might be harmful for human operators. Their operation requires a full autonomy, and one of the main challenges of the autonomous navigation is obstacle detection. Cameras have proven to be an information-rich, affordable, and lightweight sensor which is beginning to dominate as an obstacle detection mechanism in the maritime domain. In order to perform the actual detection, it has to be coupled with some sort of computer vision algorithm. Recently, deep semantic segmentation methods have proven to be very successful for these tasks on a related domain of autonomous ground vehicles. However, a recent study has shown that these methods cannot be readily applied to the aquatic environment, where they underperform by missing obstacles and detecting a lot of false positives. So, a specialized architecture is required. For this purpose, we have developed a novel deep segmentation network, which is also our first contribution. Its architecture consists of a deep encoder, which extracts rich features from the input image, and a decoder, which is in charge of three tasks. It fuses inertial and visual information, it increases spatial resolution, and it produces segmentation output. Our second contribution is fusion of inertial information and visual data. Using inertial data obtained by the onboard IMU sensor and an efficient camera IMU calibration, we estimate the horizon location in the image. The horizon provides constraints for the location of the sky and water component in the image. We encode its location in a discretized binary mask and introduce it to the network as an additional feature channel, which is fused with the encoder features at multiple levels of the decoder. Since encoder features and inertial features are at different scales, we propose applying a tension refinement model, ARM, which learns to adjust the fusion weights. Similarly, the feature fusion model, FFM, fuses low-level and high-level features in the proposed network. The final, a true spatial pyramid pooling, ASPP model at the end of the decoder is used to capture wider global context. Our third contribution is a new water obstacle separation cost function that aids learning of features. In a recent study, we have observed that water appearances like glitter and object mirroring pose a significant challenge to water segmentation networks. While mistaking water for sky does not pose a threat, mistaking obstacles for water and vice versa does lead to a potential USV collision or frequent false alarms, rendering the network useless for practical navigation. To avoid this, the network should ideally learn encoding in early layers such that it produces very similar features for a variety of water appearances and very different features for obstacles. For example, here are shown the initial features of different semantic components which are all mixed together. But using our proposed water obstacle separation loss, we can cluster the water features into a tight cluster that is well separated from the obstacle features. This separation also makes the subsequent learning of the classifier in the higher layers of the network easier, and it utilizes better the capacity of remaining layers. WaSR was trained on a segmented maritime dataset, master 1325, and evaluated on a very different and separate dataset, MODD2, using standard evaluation metrics. The performance was compared to state-of-the-art autonomous ground vehicle segmentation networks, and the results are shown in this table. WaSR significantly outperforms the other methods in water edge estimation, as well as in obstacle detection, where it detects the highest number of true positives and the lowest number of false negatives. This subsequently leads to the best overall F-score. Here are some qualitative examples of the top 3 performing networks. In the first row, we can observe that our network is capable of detecting a buoy surrounded by sun glitter and environmental reflections, while other networks aren't. In the second row, we can see that WaSR detects significantly less false positives in the presence of haze. This video shows a side-by-side qualitative comparison of WaSR and second best performing method, BSenet. BSenet detects a higher number of false positives triggered by sun glitter as well as haze. We can observe that WaSR significantly better estimates the water edge and also better localizes the obstacles. In order to gain additional insight into the contribution of each novelties, we have performed an ablation study. First, we have analyzed the importance of the inertial data fusion by omitting it from the network. The water edge estimation accuracy has deteriorated severely, which is seen in the first, second, and fourth column. The overestimation of the water edge seen in the first and fourth column are examples of dangerous misclassification where distant island is labeled as C. The amount of detections has reduced, making the network more dangerous to use. However, we observe a decrease of false positives triggered by wake as seen in fourth column, but this is merely a side product of a poorer water edge estimation. We conclude that the inertial data fusion is in fact important and its contribution is most apparent when the USV faces the open water. Next, we have analyzed the importance of the water obstacle separation function by omitting it from the network. The overall performance severely deteriorates. Water edge estimation accuracy decreases, as well as the amount of true positives, while the amount of false positives increases. In the third column, we can observe an overall worse segmentation accuracy of nearby large obstacle, which also affects the water edge estimation, while in the second column, a misclassification of a small obstacle can be seen, which might lead to a potential collision. We conclude that the water obstacle separation function is in fact important and that its contribution is most apparent when the USV faces towards mainland or large objects. Since the publication of the paper, we have also analyzed the generalization capability of the three top-performing networks, where we have selected challenging sequences from the Singapore maritime dataset, which was captured in Singapore using completely different acquisition setup. We can observe a good segmentation results from all three networks on the night sequence, even though there weren't any night shots in the training dataset. However, in the presence of prominent wakes and sea foam, only our proposed network is capable of correct segmentation, while other methods produce a significant amount of false positive detections. So to conclude, we have proposed a novel deep segmentation architecture specifically designed for unmanned surface vehicles. It fuses inertial measurements and visual information in a novel way to constrain the location of the water component and achieve better segmentation in the presence of visual ambiguities. The proposed water obstacle separation cost function applied early in the encoder helps the network learn such encoding that it produces very similar features for a variety of water appearances and very different features for obstacles. This improves the overall segmentation quality of the water component and leads to a better obstacle detection and localization. We have evaluated the proposed network on a maritime benchmark using standard evaluation metrics, where it has significantly outperformed state-of-the-art segmentation methods in water edge estimation as well as obstacle detection. Its capability of generalization was analyzed on challenging sequences from the SMD dataset, where it has also achieved astonishing results and outperformed other networks. However, WaSR also has its drawback, which is speed. Therefore, we will focus our future work on further speeding up the segmentation while maintaining the accuracy.